I hope I'm recording. Yeah. Okay. Non-circular accelerator. Well, we do have. I mean, Stanford got a linear accelerator. Oh, you mean the actual Salmon Island? Yeah. Yeah, yeah. Linear accelerator. Okay, so let's go to full screen and we shall continue. We will try to finish chapter 8 now. Chapter 8 is kind of a short topic with more difficult things towards the end, so I don't know how long or how short we will be. And then after that, chapter 9 about waves is a longer chapter, so we will probably spend more time talking about chapter 9. So, but now we are halfway through the story about pendulum. In our previous class, right, we were talking about the pendulum, the simple pendulum. So it's just a string and the mass at the end. And then what if I do not use a string? So any general object, right? So any object or any general shape, right? If you pivot it somewhere, right, you can swing it like a pendulum as well. So this is something that can also oscillate, and right now we will try to study this type of object. So any object of any shape, right, it can behave like a pendulum. So we want to see how we solve this type of cases. So let's say I have an object of any shape, right, and total mass is m, okay, and then the moment of inertia of this object is I, and moment of inertia around the pivot, okay. And then let's say my center of mass is here. So if my center of mass is here, right, if I push this a little bit, the center of mass will oscillate and the whole thing will oscillate, and we want to calculate the frequency of oscillation. Okay, so how do we study this system? And as always, right, if we know the center of mass, we can treat all the forces in relation to the center of mass. So we treat it like a point particle and we solve Newton's law using the center of mass. Okay, so what are the forces acting on the center of mass for this type of situation? For this object, there is only one external force. There is only the weight. There's only the weight, mg, right? So mg. And then what I really want for the pendulum, right? For pendulum, just like last time, we want to study the case that is tangential to the orbit, tangential to the circle, right? So the motion of the center of mass, if it's oscillating, is oscillating around the section of a circle. So what I want to do is I will resolve my weight towards the tangential direction, and it is going to be mg sine theta. So now I'm taking this theta to be my angle, right? And just like before, I will again take the small angle approximation. So there is only one force to study here. So there's only one force. So what is the torque acting on the system? So the torque, right? So let me say the distance d from the pivot to the center of mass is this distance d. So the torque on the object is well, it is the force times the distance, right? So it is this force, the linear force, and then times the distance, and this is the perpendicular distance. So it's mg sine d, right? So I'm going to take anti-clockwise to be positive. So if I take torque by the rotational Newton's law, the torque is equal to I alpha, right? And then the torque is given by this, so is this way will be clockwise torque, so it's negative mg sine theta times d, and is equals to I times alpha. So remember what is alpha here? Alpha is the second derivative of angular displacement, right? So we got this now, and then just rearrange this a little bit. I got m times g times the distance times sine theta, and then this is I d theta dt square. Okay, so rearrange this one more time. So d theta dt square is negative mg d over I, and then sine theta. Okay, so again I'm going to do the small angle approximation, same thing we did last time. So we will consider theta is small. So if theta is small, right, then my sine theta, well, sine theta is the series, is theta over theta 3 over 3 factorial, theta 5 over 5 factorial, right, 7 over 7 factorial plus dot dot dot. But if theta is small, this one we can negligible, right, we can neglect, so it's negligible. Okay, so sine theta is approximately equals to theta, right? So my equation is approximately second order d theta dt square. So the sine theta is the same, is approximately similar to theta itself, so it's mgd over I times theta. Okay, so now we get the simple harmonic equation again. So if you remember, right, when we are when I first show you the simple harmonic equation, right, so the second derivative is negative constant, and I was using x, and then we got the solution where xt is equals to a cos omega t plus phi 0. So this is the same equation as my simple harmonic equation. So if I compare the two, right, so if I compare the two, I conclude that this is the same equation where my angular frequency is mgd over I. Okay, so comparing the two equations, right? So and then these are just different names of the variables. Okay, so just the dummy index. Then the omega that we have found is the square root of mg times the distance over I square root, right? So from omega we can calculate the frequency because omega is 2 pi f, and at the same time omega is 2 pi over the period, so we can get whatever quantities that we want. So for example, the frequency is 1 over 2 pi mgd over I, and the period is, we can calculate using 2 pi moment of inertia mgd square root. Okay, so this is the frequency of the or period of the physical pendulum. Of the physical pendulum. Okay, so I think if you just remember this, or just starting with this, you can get all the other quantities already. Okay, so this is the physical pendulum, right? It looks difficult, but at the end of the day, after we calculate, you just get this formula. Okay, so yeah, is it clear so far? Or you guys are talking about island? Yeah, Xiamen is an island, right? And then there's a bridge to the mainland, and then there's a city in the mainland also, right? Oh, okay. Yeah. So everyone follow so far, right? Physical pendulum is not as difficult as you think it is, because at the end of the day, it's just this formula. The only challenge is to remember that when it comes to physical pendulum, right, you need to get the correct distance d. The distance d is from the center of mass, right? And then also, given a different situation, you may need to calculate the moment of inertia properly. So let us see how to do this by several examples. We start with a simple one. Okay, so in example 8.4.1, right, it's just nothing but a uniform rod. So let us see how the uniform rod works. Right, a uniform rod. So uniform rod is basically, yeah, every time we deal with rod, right, our common object that we always study, right? So if I have a uniform rod of length L and mass M, right? And then if it's uniform, so it's something like this, right? And then you just swing, and then you calculate the frequency of this oscillation. Okay, so this uniform rod will swing back and forth, and we want to calculate what is the frequency of oscillation. So how to study this? If it's a uniform rod, the pivot is attached to the end. So what is the moment of inertia? Right? Even if you don't memorize, right? If you do it a few times by now, also I remember, right? Some 1/3. If it's center, it's 1/12. Right? And then what is the distance? So the distance is the center of mass to the pivot. So the pivot is here, the center of mass is over here, so the distance is L over 2. So I got L over 2, right? So what is the period of this uniform rod oscillation? So using the general formula is 2 pi I over m times g times the distance d, right? So for this question, my moment of inertia is 1/3 ml square, and then the mass is mg, and then the distance is L over 2, okay? And then you square root. So cancelling these two terms, and then just simplify, then you got the answer, right? So the 2 I bring to the top, 2, 1 of the L will cancel, so it's 2L over 3G. Okay, so that is the period of oscillation for a uniform rod. Okay, so very easy, right? You can get more and more complicated shape, but always remember what is the center of mass, then make sure you get the correct moment of inertia. For the phone effect, the center of mass, so there's 2 points, right? There is a pivot and there is a center of mass. So if I take a phone, right, so maybe this is more or less uniform, so the center of mass is right at the center, right? But if I pivot it, let's say somewhere here, right, so there's a distance, right, center of mass here and the pivot here, right? So it depends on the distance between these 2 points, then it will oscillate. Okay, so and that brings us an interesting case to study. What happens if my pivot is the center of mass? So if the pivot is my center of mass, right, that means D equals to 0. D equals to 0 means omega equals to 0, right? So it's 0 frequency. So 0 frequency means there's no oscillation, it's just constant if I grab it at the center, right? So that is one, that's an interesting way to check, right, the solution. What happens if D is 0, right? The pivot at the center of mass. But generally the pivot is not at the center of mass, then it will start to oscillate. Yeah, D0 means no pendulum. Because if we want to draw the free body diagram, right, because we are drawing the free body diagram, so the free body diagram, the center of mass is the important part, right? So we can consider the forces acting on the center of mass. Yeah, so that we can treat this as a mass and then just draw one force, and then ignore all the other internal forces. Okay. Okay, so let me pull up the example for the dinosaur, right? Dinosaur. Yeah. So this is actually kind of interesting. How do people know how fast do dinosaurs walk? Because all the dinosaurs are extinct, right? So we cannot observe a live dinosaur. Everyone is dead. Then how do we know how fast can a dinosaur walk? They actually do it by studying the footsteps. So according to this question, right, all walking animals have a natural walking pace, number of steps or minutes that is most comfortable, and we will assume that this is corresponding to the oscillation frequency of the physical pendulum. So using the formula that we derive, so that should be that should determine the natural pace of the dinosaur. So how does this pace depend on the length from head to the foot? Assume this is a uniform rod. Well, we have already calculated this, right? The question is not clearly worded, it's from the textbook, but we have already calculated the period of the uniform pendulum. Then for fossil evidence, the length of the dinosaur leg is 3.1 meter, and the footsteps is 4 meters apart, right? And then we estimate the walking speed. So let us solve this. Okay, so 8.4.2. Question A is just asking for the period of the walking step, and then we are assuming that the leg of the dinosaur is a uniform rod. So we already calculated the uniform rod here, right? The period is 2 pi, so it's 2 pi 2L over 3G, right? So this part is straightforward, okay? And then for part B, right, we want to calculate the walking length. So the idea is this, right? So we are assuming that from one step to the next step is one period, and the distance is the distance between the footprints. So in one period, okay, so in one period, the footsteps, right, is a distance of 4 meters. So it covered a distance of travel, right? So next footstep is at a distance of they call it S is equals to 4 meters, right? And then from here we can calculate the speed. So the walking speed, I'm gonna call this V, is just the distance S over the period T, right? So from here we can estimate the length. So for the case of T, right, for the T-Rex period of where the leg is 3.1 meter, T is 2 pi 2L over 3G. So this is the formula. So if we put in the numbers, it is 2 times 3.1 length of the leg, and then 3 times 9.8 of the gravity. So from here you get 2.9 seconds, right? So the answer is 4 meters divided by 2.9 seconds. So in the end is 1.4 meters per second. And 1.4 meter per second, to make it more familiar to our everyday measurements, is 5 kilometers per hour. So a dinosaur typically walks at about 5 kilometers per hour. Oh, yeah, so you scale it from a chicken, if you assume the linear scale. Yeah, so the constant will depend, right? So you can, one way you can do is, so like, how to say, the walking speed, right? So the walking speed of chicken, right, and then walking speed of T-Rex, and then if you're assuming a linear scale, right, then you need to get the constant, right? So constant, so the V of the animal is the constant of the compared to the chicken constants. Then you need to determine the proportionality constant, and to determine the proportionality constant, you need to do experiment to get the other animal. So let's say eagle or something, I don't know, right? So then you can plot the graph to get the proportionality constant, and then you extrapolate. So yeah, that is probably another way to estimate. Thick ties. thick tie Rex. Yeah. THICC, right? Nowadays people like to say. So let me add a few more examples. Just now, right, is just a simple example for uniform rod. So let me add a few more things. Let's say I consider some other problem, a disk. Okay, so how do you calculate the frequency of a disk? So let's say I hang a disk, right? So let's say you have a CD. I think in 10 years ago, 20 years ago, right, a lot of the houses, people, they like to decorate the house using the old CD. They like to hang, right? So they take an old CD, they hang, and then, yeah, that's the decoration of the house. So if I take a CD and hang it, right, so I have a disk of radius R, and the mass is M. Okay, so let's say I have a uniform disk. So the radius of this disk is R, so is R, and then let's say the mass of the disk is M. Okay, so how do you calculate the oscillation over here? We got the formula already, right? The formula is everything. We just need to know what is the D and what is the I. Then we put in the rest accordingly. Okay, so for the uniform disk, well, first thing, right, we do know the moment of inertia when it is passing through the center of mass. Okay, what is the moment of center of mass? Is half mr squared. But the pivot here is not on the center of mass, right? do you remember what we are supposed to do? We are supposed to use the parallel axis theorem. Okay, so this is the important point. You need to use the correct moment of inertia, right? So according to the parallel axis theorem, the moment of inertia is for a new axis is plus md square, right? So I shift this, so from here to here is r. So my moment of inertia that I should use is half mr square plus m, and then the distance square is just r, so it's r square. So my new moment of inertia is 3 over 2 mr. Okay, so I got my moment of inertia already. How about my distance d? So the pivot from the center of mass, the distance is also r. So my d is also equal to r. So from here I can calculate my frequency of oscillation. Start with omega. It is mgd times divided by I. So it's mgd. D is r. And then I is 3 over 2 mr square. And then square root. Right, so I cancel the r, I cancel the m. So this is 2g over 3r. And then square root. So this is my angular frequency for of a disc pivoted at the edge. Okay. The discs. Yeah. Is it to prevent fly? I don't know. It's just a CD, right? Yeah. Last time when I was younger, if I go to people's house, sometimes I see some people do that. In Pasar Malam also. Yeah. Fly probably won't care. It's just the plastic, so it's not doesn't make much of a difference. Okay. So everyone understand this part, right? Everything is clear about this? Okay, so let me make it more difficult, right? So let's say, right, I do a more complicated shape. Okay, so my more complicated shape is this. So I have a pivot, I have a uniform rod. Okay, so the mass of the rod is m, the L, and then at the end of the rod, right, I attach another disc. So let's say, for make it simple, the disc is also having mass m, and then the radius is r. So can you calculate this case? What is the frequency in this case? So we need the moments of inertia, right? So the rod is okay, right? The rod is fine. The I rod is 1 over 3 ml square. There's no problem there. The moment of inertia of a disc is what? Well, it is the center of mass is half mr square, but my axis is not on the center of mass. My axis is here, my pivot, right? So I need to use parallel axis theorem. So I need to plus m and then the distance square. So what is the distance I should use? Okay, so if I join this at the center, then the distance shifted is L. Am I right? Okay. So the moment of inertia of my disk is half m r square plus L square, right? So yeah, correct. R square plus L square. Okay, so I got the moments of inertia and moments of for the rod and for the disk. So the total moment of inertia of the system is rod plus disk. So we got 1/3 ml square, and then plus half mr square plus another half ml square. So this term will give me 5 over 6. Am I right? So 5 over 6 ml square plus half mr square. So this is my total moment of inertia. Okay, so did I do something wrong? Why is there a half? There shouldn't be a half, right? So this part is totally wrong. Yeah. Why do I factorize this out? So this is half mr square plus ml square. So there's no half here. So this is 1/3 plus 3 over 3, so it's 4 over 3 ml square. Okay. Now what else do we need? We need to know what is the d, right? So what is the distance d? The distance is the distance between the pivot and the center of mass. So what's the center of mass? Over here. We need to calculate, right? So the center of mass of the system is, well, I have a rod attached to a disk. Okay, so this is the center of mass of the disk. And then this is the center of mass of the rod. So center of mass of the rod is at L half. And L half. And then the disk is over here. Okay, so then I need to get the total center of mass of the system. So the center of mass of the total system is xcm, right? Remember the formula. It is the mass of this object. So the mass of the rod is m, and then the center of mass is, let's say this is my origin, right? So x over 2. So it's m plus L over 2, and then the center of mass is the mass over here, and then what is this distance from the axis? So the distance is just L, right? So it's L, and then I'm dividing by the total mass m plus m. Okay, so in case you are confused where this came from, right, let me remind you, the center of mass formula is m1 position 1 plus m2 position 2, and then m1 plus m2. Here m1 and m2 are the same, is capital M, right? Position 1 is L half, position 2 is totally L over here. Okay, so just calculate everything. Downstairs is 2m, half plus 2 over 2, so it's 3 over 2 ml. So cancelling, I got 3 over 4 L. So xcm is somewhere over here. Okay, so that means the center of mass system is at the position 3 over 4L away from pivot, right? Because that is the distance from the pivot. Do you agree? Page 2, page 3, page 4. Okay. Yeah, that's the wrong. Yeah, I corrected this already. Right. The ml square is parallel axis theorem, yes. Am I recording? Test. Yeah. So if everyone is agreeing, right, then yeah, that's the solution already, because we just need what? The I, and we need the D, right? So we have these two things already. Then from there we can put in the formula to calculate the angular frequency. So the challenge is to determine the moment of inertia and the distance. So now let us put it into the formula. Because our formula is omega is the total mass of the system, and then g, and then the distance over the I. So another thing to be careful about, the total mass of the system has a rod plus the disk, so totally is 2m, and then g, and then the distance is 3 over 4l, and then divided by moment of inertia is this number, so it's 4/3 ml square plus half mr square. Okay, so we can try to simplify the best that we can. This cancels, becomes 2, so it's 3 over 2 mgl, right? And then I got 4/3, so let me take out 1 over 6, so this becomes 8 ml square plus 3 mr square, and then like this. Okay, so I can actually cancel away the m. Most of the time the m cancel each other in the equation, and then I got 6 times 3 over 2. So I'm very bad at mentally cancelling this, so I must be careful, so just write one more step to be safe. So it's 3r squared. Okay, so this cancel becomes 3, so upstairs becomes 9. So 9gl over 8l squared plus 3r squared. So that is my angular frequency. Okay, so if I want to get the period, then the period is just 2 pi over omega, right? So just 2 pi and then just flip this. So it's 8l squared, 3r squared. So once you get the omega, you can easily calculate everything else. Like this. Okay. So yeah, physical pendulum, very simple. You just need I and then the distance. So just make sure you calculate the distance correctly. Okay. Any question? If not, then we are going to go to a different topic now. Last two types of oscillations. So this one, right, in the next topic I will actually just cover briefly, because the mathematical details will teach you more details in the math course. So you will be taking the MAT 108 differential equations. The math students are taking them now, right? So you guys probably know what I'm talking about. Okay, so the next topic is damped oscillations. So basically, right, I have oscillations with a resistive force. Okay, so resistive force, if you remember, it is drag force. So let's say I consider, when we were talking about harmonic oscillator, right, we were talking about a box of mass m and it's attached to a spring, right? So if the equilibrium position is here, then the spring will pull it back, right? It's always opposite. It's always pulling the box towards the equilibrium position. So the magnitude is kx, the direction is here. Okay, and then so the motion, last time we were assuming that the floor is smooth. But what if the floor is not smooth, or if there's air resistance? So let's say I have some kind of air resistance over here. So the air resistance will give us a drag force, right? So the drag force will become, the drag force is in terms of, let's say, kV. Okay, so if the drag force is velocity dependent, if the box is moving in this way momentarily, the drag force will be this direction. If the box moving the other way, the drag force is in the opposite direction. Okay, so let us take this as my drag force. So what is the net force acting on this object? So by Newton's law, F is equal to ma. Over here, the Hooke's law gives me a negative kx, right? Negative because it's always negative to position. The drag force is also negative kv because it's always negative to velocity. Okay, if velocity is positive, the drag force is negative. If velocity is negative, the drag force is positive. Okay, and this is equal to ma. Okay, so that is my so-called equations of motion. Okay, so now let us express this as a differential equation. This is actually an equation for x, because my velocity is dx dt, my acceleration is the second derivative x over t. Okay, so let me rearrange everything. So I bring everything to be positive. So m d2x dt square plus oh, hang on, I use k in two places. That shouldn't, that's confusing, right? Let's call this b. Okay, so let's call this b. This is b. Yeah, cannot use k for two things. So b, so I got b dx dt, and then plus kx. Okay, so this is b, this is b, b times v. Okay, so drag force is negative bv. Okay, so if I think you agree with kx, right? The sign of kx is negative because it's always pushing it back to the equilibrium. The sign of bv is always opposite to velocity. The drag force is always opposite to velocity. The direction of drag force is always opposite to velocity. That's why this is negative. The kx is Hooke's law, right? The sign of the direction of the spring force is negative to the displacement, always. Right? So remember, we did this in when? Chapter 2, is it? Yeah, you remember? I did not draw this in the lecture notes. Yeah, we did this last time. Yeah, so you remember this? See that here is called K. The drag force is negative. Okay, yeah. So there are two separate reasons, because they're always opposite to things. So, but at the end of the day, right, we got, so now we shall assume M, B, and K are all positive numbers. So this is a differential equation. So the MAT students they have already learned how to solve this equation. I asked your lecturer already, right? Dr. Lin Taoshuan. He told me you guys should be able to know how to solve this. But the physics student don't know yet. So you guys will take this course in the next semester, if I remember correctly. So the Dr. Lin Taoshuan will teach you how to solve this equation. I will just show you the solution, and what we will do is to just check whether this solution is correct or not. Okay, so this is a differential equation. It's a second order linear ODE. Okay, so I'm going to give the general solution. Is given by, I claim that my general solution is it has some constant amplitude, right, and is also expecting to have some hang on a second. Okay, so cos omega t plus phi 0, and then e to the negative alpha t. Okay, so I claim that my general solution, is it this one? Okay, so is it this one, right? So let us check. Okay, so let us check the So let us check this solution. Okay. Yeah. So I'm trying to decide how much math I want to go to. Yeah. Let us let us work it out, right? So yeah. So don't worry about exam you being asked this kind of thing. I will show you the math. Is only to because even though it's not come out in the exam, it's important to convince yourself that it's a solution. So I will do the calculation here, right? So I want to substitute this formula for x into this equation, and let's check when can I get the solution. Okay, so is this a solution? So let us check. Okay, so well, I will need the derivatives. So the derivatives is, if I differentiate x with respect to t, I have now a product of two terms. So differentiate the exponential, I got negative alpha e alpha t cos omega t plus phi 0, And then differentiate omega, I get negative AE alpha t. Omega comes out and then becomes sine omega t plus phi 0. So I can simplify this a little bit. I am going to get A E negative alpha t, and then this one take out the bracket, and then inside is alpha cos this thing, and then minus omega sine of this thing. Okay, so this is the first derivative, and then I will skip some steps because again I shouldn't spend too much time on the math. The second derivative, so let's try to, and it's for you to practice your calculus, right? The second derivative is going to be like this. So the second derivative is AE alpha t. So after you differentiate everything, right, you're going to get this thing. Okay, plus alpha omega sine omega t plus phi 0, and then omega sine omega t plus phi 0, and then minus omega square cos omega t plus phi 0. So my second derivative is, I can simplify to alpha e alpha t, and then I can group together the common terms, alpha squared minus omega squared cosine omega t plus phi 0, and then this plus this gives me a 2 alpha omega sine omega t plus phi 0. Okay, so I got this thing now. So I'm going to substitute. So I have my x, my first derivative, and my second derivative. So I'm going to substitute into the ODE. Okay, so substituting into the ODE, I got well, for the first term is m times all this. So I got m a e alpha t alpha minus omega cos omega t plus phi 0, this thing sine omega t plus phi 0, and then the second term is b times the first derivative. So b times this, so it's b a e alpha t times minus alpha cos omega t plus phi 0 omega sine omega t plus phi 0. Okay, and then the last term is kx, so k times this, so I plus k a e alpha t cos omega t plus phi 0, and the whole thing is expected to be equals to 0. Okay, so let us see our solution, right? Actually we can simplify because a times exponential is everywhere, so I can take it out and then it will be disappear after I factorize it. Okay, and then the cosine terms, right? The cosine terms is this term, and this term. So the cosine term is m alpha squared minus omega squared minus b alpha plus k. So all these are cosine terms. Okay, and then my sine terms are here. So don't forget the m, right? So the m times this, I got 2m alpha, 2m alpha omega, and then minus b omega. Omega t plus phi 0 is equals to 0. Okay, so let me check if I made any mistakes. I think it's correct. So how do I make sure that this equation is really equals to 0? Okay, so if I want this to be really equals to 0, right, then okay, let's make the coefficient equals to 0. So if I want this to be 0, I got 2m alpha omega must be b omega, right? So the omega doesn't matter, so I conclude that my alpha is b over 2m. Okay, and then if I want this to be 0, so I got m alpha squared minus omega squared minus b alpha plus k. I want this to be 0, and then I have alpha given by this over here already. So I got m alpha squared is b squared over 4m squared minus m omega squared and then b times alpha, so it's b squared over 2m plus k equals to 0. So what do I have? I have m omega squared, and then this thing here, and then bring it here. So I have a quarter minus a half, so I get negative b squared over quarter, right? Plus k. So finally I conclude that I got k over m minus b squared over 4m. So I have found the frequency of my solution, and this solution, apparently there's a square root, so to make sure that this is correct, this is valid for as long as this term is positive. So it's k over m is greater than b squared over 4m. Okay, so I have found my solution over here. Okay, so actually I got the solution that is only satisfied for this case. Hang on, I am missing a sign. I am missing a b squared. Wait, I did something wrong. Where is it wrong? Oh, if I divide the m down, k over m, this is m squared. Yeah, so it's as long as k is greater than b squared over 4m, or in other words, b squared is smaller than 4mk. Okay, so yeah, so this is how I just want to show you like usually what people do in physics, right? So we got a solution, and then usually you want to check whether something is a solution or not. So you put it in, you run through the calculation, make sure everything equals to the right hand side. So to make sure this equals to the right hand side, I have fixed my constants. So my alpha is given by this, and my beta must be smaller than this to be true. Okay, so that gives us the different cases of the oscillations. So let me categorize them for you. Okay, so again, right, this one, don't worry about this. I just want to show you only. Okay, what you really should learn, that is the more important part, is the different cases. Okay, so there's two different cases. The one that we just checked just now, right, is what we call case 1. It is the under damping. Okay, so under damping is the case that we have just checked, is b squared is 4mk. Right, so remember what was b? B, right, is related to the drag force. Okay, so if the drag force is relatively small, it's still a damped oscillation, so it's still quite small. That's what I'm trying to say, right? So it's still quite small. Then the general solution that we have found is x of t. It was the one that we have checked, is a e negative alpha t cos omega t plus phi 0, right? And then the omega we have found is given by this thing. So let me simplify this a little bit more. So let me make all the denominators the same. So the downstairs is square root of 4m squared. So after you take the square, it becomes 2m, and then it becomes 4mk minus b squared upstairs, right? And then your alpha was b over 2m. Okay, so wait, is anyone confused yet? Should omega square root? Oh yeah, I forget to square root. Yeah, so I write extra square. You're right. Yeah, you're right. Okay. So actually, right, this under damping case, what does the graph look like? So the graph, right, actually is like this. So it's still like a cosine function, but the amplitude is decreasing over time. Okay. So the way to draw this is, okay, I have an exponential function, so it's the amplitude is like this, right? And then cosine can be positive or negative, so I draw the same for the negative side. Okay, so what is happening here is that my graph is oscillating between the exponential graph, so it's like here. So it will reduce and eventually die down to 0. So this is why we call a damped oscillation, right? So if there's friction in the system, energy will be lost, so the oscillation will be smaller and smaller and smaller and smaller until it goes to 0, right? So this is the under damping case. Okay, so makes sense, right? Follow so far? Okay, so sometimes this graph, right, is called the envelope because it is containing the rest of the graph inside here. Okay, so this is my under damping case. So for case 2, right, let's consider the second case is over damping. So this one is because the friction is still weak, so it can like gently slow down the oscillation until it becomes 0, right? But if the friction is very strong, more specifically, it is greater than 4 mK, right? It's greater than 4 mK. This is something that you will learn in MAT 108. The general solution is given by a constant and exponential, so alpha negative t, and then another constant and alpha positive t. So what is alpha positive and negative? Alpha positive and negative are given by b over 2m plus and minus b squared minus 4mk square root, right? And then this is 2m. Okay, so both are exponentially decreasing solutions. So this is what we call an exponentially decaying solution. Okay, so if you try to plot the graph, right, it's going to look like this. So it will just like it's just like die down. Okay, so it doesn't even have a chance to oscillate because the friction is so strong, right? The resistive force is so strong, it will just like immediately slow everything down to 0. Okay. No, alpha times t times. Alpha negative times t. Okay. Yeah, so if you will learn this in the the math course, right? So I'm just mentioning the physical properties only, right? So if the friction is small, then yeah, it will slowly slow it down over time. If the friction is too strong, then it will immediately slow everything down quickly, right? And then the case 3 is nothing special. It's what we call critical damping. Is the case in between these two cases because I have smaller than 4 mK, greater than 4 mK, so this is equal to 4 mK. So critical damping is b squared is equals to 4 mK. So this one is nothing special. You can't really tell much of a difference. I think if you plot the graph, right, it will probably look something like this. And then some, so it's in between this to this. Okay, so I will show you the more nicer looking graphs than what I drawn later, because now I think it's a good time to take a break. Okay. Actually, yeah. Calculus 1 also they learn OD. Calculus 1. Hang on. They actually no. Maybe calculus 2. Maybe calculus 2. Yeah. So, by the way, I will stop the recording first, and we will take 10 minutes break. Okay, so now with the equations that we have derived, right, I was like simply drawing some ugly pictures, but what I can actually do is to use a computer, since I'm at a computer right now, use a computer to actually solve this equation. So and then I will show you how the graph looks like. Okay, so let me capture this on the OBS. Hang on. Please. Okay, so I think this, yeah, so it will be recorded in the video later. Yeah, something like this, and then I will show you in the full screen. Okay, so remember, right, so my differential equations, full screen, sorry, full screen. My differential equation is this, right? So it depends on m, b, and x. Okay, so in particular, my three cases are: the case 1, under damping is b squared over 4mk, over damping is greater than this, and then this one. Okay, so let me try an example. So let me put an example for the damped oscillator, right? For the example, let's put a simple simple to calculate is m and k equals to 1, and then I'm going to put b is equals to 0.3. So that in this situation b squared is definitely smaller than 4mk, because 4mk is 4, right, and 0.3 square is 0.09, so it's a very small number, so it will satisfy case 1. Okay, so let me put this into the simulation and let's see what we get, right? So so b is 0.3, m is 1, k is 1. So let me compile, and then let's see how the solution looks like. Okay, plot solution.dat using 2, 1 with lines. Okay, so as you can see, right, after a long time, my oscillation eventually will die out, but the initial time is, let me zoom into this part, right? So I start from this oscillating a spring, and then as you can see, it is following the exponential envelope, so it will oscillate like this and then slowly die down to 0. Okay, so this is the under damping case, right? So this is the under damping case. So let me look at the over damping. So for over damping, right, let me go back to the full screen. Oh yeah, it's not showing here, I forgot. Let me put this in front. Okay, so for the over damping case, the example I want to show is, let me write down example, mk equals to 1, and then b is equals to 3. So if b is equals to 3, it's going to be much larger. See, too many windows, I'm confusing myself. So let's put b equals to 3 and see what happens. Okay, so I will compile the code. Okay, and output to then plot this graph. Okay, plot. Okay, so yeah, it's not very let me zoom in a bit. Right, so immediately die down straight to 0. So this is where the friction is very high. When the friction is very high, everything goes down to 0 very quickly. Okay, so this is over damping. And then the case of critical damping is not very boring because it's just in between the damping, under damping and over damping. So if m and k are equals to 1, right, 4mk is 4. So b squared, I want b squared to be 4. So b is equals to 2. So this is critical damping. Okay, let's see how the graph looks like. Plot using 2, 1 with lines. Okay, it's very similar to over damping, right? It's can't really tell much of a difference, right? It almost wants to oscillate a little bit at the bottom, but it goes to zero very quickly as well. Okay, so yeah, so those are the cases. It's too big. Never mind. Yeah, so if this one is okay, so so basically we are just I'm using a computer to reproduce all these situations over here. Any questions so far? Thermal got PDE. No, not really, but got partial differentiation. So PDE is partial differential equation. Those are different story. Yeah, partial derivatives. I think my hand overshoot lah. So yeah, my hand overshoot. So yeah, don't care. The critical damping is this one, right? So that's why I use the computer. It's more clearer. Using 2, 1 with lines like this, because sometimes it will overshoot the bottom depending on the frequency of oscillations. Will it? Will it not? I'm not sure. Yeah, but in any case, yeah, that's the critical damping. Okay, so exit first. We're gonna come back to this later, so I'm gonna keep it there for the moment being. Internal. I mean, it's not that bad lah. Actually, the partial derivatives in thermal physics is easier than other places. I think if you don't like partial derivatives, right, you will hate electromagnetism more than thermal physics by comparison. So that was about the wait, I can't find my notes. Okay, so next let us talk about the forced oscillations. Here I'm even going to touch less about the math. Okay, and let's talk about these forced oscillations. Okay, so just now, right, we were so the oscillations that we have been studying right now at the moment we only consider two forces, the spring force and the frictional force. Okay, now let us add another external force on top of everything else, so that right now I have my net force on the oscillator. Okay, and it is now we add a new force. So just now, right, previously we consider a force due to the spring, right, and then the drag force, and now I add another external force. Okay, so so we were talking about MA, right? So the force due to the spring is negative kx, right? The reason why negative is always pushing it back towards the equilibrium position. Then the drag force, the force is always opposite to velocity, it's always against the motion. So this is negative b times the velocity, right? And now I add another force. So this is an external force. Okay, so right now what do my differential equations look like? So if I write everything right, the acceleration is the second derivative with respect to t, and then this is k x, and then this is b dx dt, and then this is my external force. Okay, so right now we just let me rearrange first. I'm going to talk about this a bit later. So if I rearrange this equation, plus b dx dt plus kx, and is equals to the external force, right? So right now the right hand side is not 0. So the right hand side is not 0. In your math courses, whether it's calculus 1 by Dr. Liu or MAT by Dr. Lim Tao Xuan, is an inhomogeneous ODE. So usually, right, you will learn more in those math courses that inhomogeneous ODE are much more difficult to solve when if the right hand side is 0, right, it's easy to solve, right? If anything non-zero, much harder to solve. Okay, so this is the external driving force, right? For the bottom right, we will consider the specific type of driving force of external force to be periodic as well. So I got sine omega t. Okay, so what if my right hand side is given by this? Okay, so this is the amplitude of external force, and omega is the angular frequency that we call angular driving frequency. So what this external force means, external force is this is a time dependent, so it is like periodically pushing on the box. So the time dependence is sine omega t, so it's like it has its own frequency as well. So there's two frequencies now we want to talk about: the frequency of the oscillation and the frequency of the omega. Okay, so if the two frequencies are the same, is what we call the resonance. If the two frequencies are different, then it is then it's sort of like against the spring, and it will sort of cause the spring to vibrate less. Okay, so the solution is again very difficult to solve, so it's a bit hard to explain without going through the math, at least for me lah. But right, for the solution, I'm not even going to show you the solution. I'm just going to show you the amplitude of the solution. So amplitude of solution is given by this formula. So it is f0, and then it is k squared minus omega squared. Wait, yeah, let's look at the lecture notes because I can't find it here. So it's k minus m omega square, the whole thing square, plus b square omega square, right? So this is the amplitude of the solution. Okay, so as you can see, right, if I plot the graph of amplitude against the driving frequency, it can go very large or it can go very small. So we can see the behavior of resonance from here. By the way, is there any questions? For electric and QM, ayo, so sad. Homogeneous only mentioned in linear algebra class. Oh, is it? Yeah, we're quite close, I think. Net external force on something that is oscillating. There's plenty of examples. The left net force is what formula? Which left? Which formula? Which left? So the net force is the sum of all the forces acting on it, right? So these are the two that we already know. I'm adding a new external force here. Okay, so yeah, a common example, right, is I think everyone will, as a kid, will play before, as a swing, right? So as a swing, and then if you sit on a swing, right, it will swing, correct? So if you just sit down and then if you give yourself some initial motion, you will oscillate a little bit. But if you're sitting on a swing, right, you can actually make yourself go further and further, right? That means increasing your amplitude. So how do you increase your amplitude? You make your body push forward, right? You make your body push forward, and then if you're going this direction, you make your body push backward. So you are making yourself swinging further and further away. Can you imagine what I'm talking about, right? So as a kid, if you play the swing, right? So if you are coming this way, right? If you're around here, you push your body forward, right? So you push your body forward, then you're giving yourself a forward force. And then when you come down, when you're coming down that time, you pull your body back, right? So you pull your body back, so you will push yourself further. So this force is also like pushing forward, pulling back, pushing forward, pulling back. It is an external force that is periodic in time. Okay, so the frequency of pushing forward and pushing back must agree with your swing frequency in order to make yourself go higher and higher up. If your frequency is wrong, right? Let's say before you reach the top, you already start to change direction, you push your body back, right? Or you do random things, okay? So if you do random things, you are not able to make yourself go higher and higher. You just slow down your swing only, okay? So this is what happens for the this solution. This is one example of a periodic driving force. Okay. So understand, right? Yeah. I don't know how common swing is, or whether there's any anybody who never played swing before. Yeah. So another example, right, is the opera singer lady. If you sing at the correct voice, right, then if you sing at the correct voice, it will break the glass, right? So what happens is that the frequency of the air vibration agrees with the molecular frequency of the glass, and then it will make the molecules vibrate a lot too much, and then if you vibrate too much until it breaks. So that is another example. Okay. Microwave and water as well. Yes, correct. This is how microwave works. So microwave also, right? So microwave is so you put your food in the microwave, right? And then the microwave actually sending microwave radiation. So the frequency of the microwave radiation is matching with the vibrational frequency of the H2O molecule, right? So it will give the additional vibrational energy to the molecule. And as you learn in your statistical mechanics, kinetic energy of vibration will correspond to higher temperature. So it will heat up your food. So this is how Pavarotti. Pavarotti is the one of those types of opera singer that is capable of doing that. What's that? Pavarotti is a opera singer. Yeah. Why metal can put in the microwave? The high pitch singer, yeah, the classic. Metal, I don't know. It's something to do with the electrical charge, right? It will cause electricity to. I'm not very sure. Yeah. I'm not sure. It's something to do with the electricity in the metal. It will cause problems, I think. Yeah. Okay. So let me show you some examples about this in my numerical solution. So for example 1, right? I'm going to use external force of 2, and then omega is equals to 1, and then I did not put my values correctly. So m is equals to 1, b I will put 0.4, Wait, I lost my numbers. Hang on a second. So let me first try example 1, 0.8, B 0.4. So if I calculate this A, right, it's going to give you 4.152. Okay, so let's put these numbers in, right? Let's see. Let's put these numbers in. Okay, so I will put B is 0.4. And then my omega, let's try 0.8 first. And then my force is 2. Okay, so let's see what happens. With lines. Okay, so yeah, so initially it's amplitude 1, and then you're driving. Hang on a second, it's raining too heavily, so I need to close my windows. Hang on, I'll be right back. Okay, so so the formula is gives us a number that we expect, because using the formula, right, I calculated 4.152, and then according to the numerical solution, yes, the amplitude is 4.152. Okay, so yeah, so this is the case of where it's not the resonant frequency. So what happens if I am at the I didn't write down my numbers properly, but let's try some other cases. So let me go to try a different force. So let's say I have 0.3, no, a smaller driving frequency, right? So if I have a smaller driving frequency, with lines, right? So the amplitude is smaller, you see, is until 2 only. Okay, so then let me try to make it the resonant frequency now. So for the resonant frequency, right, the omega for this case is 1. So how do you get the resonant frequency? I want to make this term, the denominator, to be as small as possible. So to make this term as small as possible, right, my k is 1, m is 1. So if my omega is 1 also, right, this term is the smallest as you can, so the amplitude can be the largest as you can. So let us try omega equals to 1. So oscillation, omega equals to 1. Okay, so let us run the code and see what happens. Solution.dat using 2, 1 with lines. I keep typing the wrong command. So yeah, this is the largest that you can, right? So you have a high driving frequency. No, the resonant frequency. So the vibration is the largest. Okay. Oh, okay, that's interesting. Oh. Release electricity. Yeah. Okay, so yeah, so that's about it for the resonance. And another thing, right? Dr. Lim told me he shown you this he shown the math student this already, the video about the bridge, the Tacoma Narrows Bridge. Yeah, so if your wind vibration happens to be the same as your natural frequency of the bridge, then it will make this collapse. Yeah, so it oscillate, and if the wind is resonating with the thing, it will vibrate stronger and stronger until the whole thing is, if vibration is too high, then the whole thing breaks and it collapses. Yeah, I don't know who these guys are. Okay, so so the vibration happens in many different places, right? So we have mentioned our own examples as well: microwave, swing, and then the opera singer, that kind of thing, right? And the guitar string also. So you can actually experience resonance if your guitars, the guitar. It also happens for guitar string. So if one string of your guitar, right? If one string of your guitar, if you make it vibrate at a certain frequency that is the same as the next string, the neighboring string will also vibrate by itself without the, even if you don't touch it. So that's the resonance as well. Okay, so I will show you guitar stuff probably next week or week after next. Okay, so we will derive something about strings in the next class. Standing wave, yes, that is the next chapter. We will go to that in now actually. Well, now we have to start the chapter first, chapter 9. So chapter 9, what time is it now? Still got time. Waves. Okay, so we start by the first thing is we need to, before we play with guitar, right, we need to do some math first. So we need to talk about the wave equation. Yeah, guitar. Actually, can you see the guitar behind me? My guitar is there. Okay, where? Yeah, the black thing there. Next week. Standing wave. Yeah, when we talk about the relevant when we talk about the vibrations of string, then we can actually demonstrate some phenomena actually by using the guitar, right? And like all the tuning of guitar, right, is actually related to what we are about to learn over here. Okay, so let's talk about waves. Before we are able to understand those later parts, we need to set up our terminology here, right? So in chapter 9, what we are going to talk about are waves. So what is a wave? So the simple way to understand waves is, waves are disturbances in a medium. Okay. So waves are disturbances in a medium. And what do we mean when we say medium? This topic is very general. So when we say someone's phone is ringing, physics band, construct a band. Yeah, Dr. Gloria can play piano, so she can be piano player. Just need someone to play drums and bass and a singer, then settle already, right? So what do we mean when we say medium? Medium is anything. So usually we will consider water, right? And then later when we play the guitar, our medium is a string. And then when we talk about microwaves or light or electromagnetic radiation, these are electromagnetic fields. And then also, if you remember the news, right? Recently in 2015, we have actually detected gravitational waves. So the gravitational field can also have waves. Gravitational. So this part is also kind of interesting, because gravitational waves is generated when two black holes, they collapse into each other. So when they crash into each other, right, this phenomena is very extreme and violent. So it will cause a gravitational vibration, and it will spread out throughout the universe. And some of this vibration, they arrive at the Earth and was detected since 2015 2016, the LIGO experiments and the Virgo experiments. Yeah, those the different observatories. There's a LISA. China is planning to have a space-based detection of gravitational wave and all those things. So yeah, so these are waves. These are the waves that we are about to study here. So actually, right, waves is kind of related to what we have been doing for simple harmonic motion. So for simple harmonic motion, right, we were talking about a single point undergoing periodic motion. Okay. By the way, am I recording? Yes. Yes. What's wrong with my sound? Hello? Is my sound okay? Oh, so you can remember the value of the C note. My sound okay? Okay, good. I don't know why this is going like crazy now. Yeah, if it's okay, then should be fine. Let's continue. When we were talking about the simple harmonic motion, right? We are talking about a single point undergoing periodic motion. So one point undergoing periodic motion. So one particle going up and down or horizontally or whatever, right? Is periodic motion, repeating. For waves, what do we mean is, well, waves is many points. In fact, infinite points. Undergoing simple harmonic motion. Okay, so I have not just one point but many points. So all of them are going up and down, vibrating. So each of them are going simple harmonic motion. Okay, so many points. All of these points are going up and down, right? So in fact, they are going up and down in such a way that there's a certain pattern to the shape. So, and then we can see how the shape changes with time. So that is the interesting and nice to look at when we look at waves. Okay, so another way to interpret waves is, well, these points is what we will take as the medium, and it is some vibration that is spreading throughout the medium. So we can imagine waves as a disturbance propagating through a medium. Okay, what time is it now? The rain is very heavy. I think my house should be okay. Yeah. So yeah, how about everyone else? Any question? Is it that for each state object has a matched frequency because of its vibration? Yeah, yeah, and it's mostly because if we talk about solid objects, then it's the molecule structure. So each molecule has a bond, and then they are connected by forces, van der Waals forces, and because of these forces, it's a restoring force, so it has some kind of vibrational frequency. Yeah. So Kaheng, you play violin, is it? Are you familiar with violins? Oh. Yeah, you're right. Rain will produce more mosquito. Oh, so you can be a guitar player also? Then yeah. So okay, so now this is just the definition of waves, and what we will do is we will study two types of waves. The first type that we will learn is the transverse wave. Okay, so what's a transverse wave? Okay, so transverse wave is where the disturbance is perpendicular to direction of propagation. So I will explain what this means. Let me write it out first. Okay, so my disturbance is perpendicular to the direction of propagation. So let us take an example. Okay, let's take a string. So let us say my string is initially at rest, right? And then this is the source of my vibration. So the source of my vibration is like maybe your hand holding onto a string, right? And then initially the string is not moving, so it's like this, okay? And then later you vibrate your hand. So if you hold the string, right, and then you start shaking your hand. So if you start shaking your hand, right, what's going to happen to the string? So the string is it will start to vibrate, right? So it start to vibrate. Okay. So if you take, because this string consists of many infinite points, right? So if you follow one point, so this point is going up and down, and then this point is also going up and down. So all these points are also going up and down. So every point of the string is going a simple harmonic oscillation. But on the far end, nothing happened yet because it's still very far away. Okay, so this is what happens. And then if we continue vibrating, right, eventually the vibration will spread everywhere. So much later, what happens? It will spread further and further. So it will vibrate up and down, up and down. Yeah, it will spread. So you see, right, the disturbance is spreading along the string. So it is spreading this way. So we can write down these two things. My direction of propagation. So this is the spreading is my propagation. So direction of propagation is going this way. And what's my direction of vibration? So every point on my string is going up and down vertically. Okay, so my direction of this disturbance is vibrating up and down. So every point on the string is either going up or going down. It doesn't go horizontally, right? So this is what we call the transverse wave. So actually, right, we can sort of imagine waves as an illusion, because if you look at the wave, right, it's like something spreading towards the right, but actually nobody is moving in the right direction, right? Every point is going up and down, right? Nobody is moving to the side, right? Everyone going up and down. But if you look from outside, it looks like something is spreading towards the right. So that is the interesting thing about the waves as well. So that's why we call it there's two things, right? Propagation and the disturbance. So clear so far? Paganini in the notes. Oh, what, did I spell it wrong? Propagation. Is Paganini another opera singer? Sounds like a name of an Italian artist. I don't know why. Okay, so that is the first type of wave. Yeah, definitely if you vibrate too long, your arms will get sore. So what is the second type of wave? So let me, before we end the class, I will explain what is the second type of waves. It's called the longitudinal waves. Okay, so for longitudinal waves, the disturbance is parallel to propagation. Okay, so just now was perpendicular, right? So the disturbance is this way, is spread in this way. So right now disturbance is the same direction. So let's take an example, air or water, right? Sound is a wave propagating. So let's see what happens initially. So let's say I have something that makes some noise, so some loudspeaker, right? And then, or Pavarotti, right? So and then the air, before you start making noise, the air is not moving. Okay, so the air is not moving, right? And then later you turn on the sound, right? So you start to make sound. So what happens to the air? So the air that is nearest will start vibrating first. This is where I wish I have a tablet so I can copy paste. takes long to draw. But later this will start to vibrate first. This will start to vibrate. This will start to vibrate. This part is still very far away, so nothing happened yet. So only much later. Right? Then copy paste. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. Right? So later this part will vibrate. Already vibrating. Then it will start to spread to the next one. So the air molecules will start vibrating, right? So it will start to vibrate. Then after that, this will start to vibrate and then vibrate. So it start to spread out, right? So it's not very clear in a picture. So let me draw the next step. 3 rows is enough. Lazy to. Okay, so this will vibrate. This will vibrate. This will vibrate. So the disturbance is spreading, right? So it's spreading to the right. So from here we can see that the direction of Pagiani propagation is spreading towards the right, and the direction of disturbance is also vibrating left and right. So it's vibrating because it's a oscillation, so it's vibrating left and right. Right, so the direction is the same, they are parallel. So this is what we call the longitudinal waves, right? So 2 types of wave, transverse waves and longitudinal waves. So there's a third type, is just a mixture of the two. Forgot to pull out the notes. Right? So the third type of wave is just a mixture, like for example water wave. So there's 2 components, so it's going up, down, left, right, but the spreading is towards the right. So you guys are talking about music. So a lot of you guys are familiar, got learned music before. Paganini is a pianist, is it? He plays violin. Okay. I mean, it's kind of similar to stats on thermal, because statistics is talking your thermal is always talking about gas, right? So yeah, this is air, so it's the kind of a similar thing, but for now we are focusing on waves over here. Okay, and actually we won't talk much about air vibration a lot. We will focus more on this type of case. Main reason is easier, is simpler, and yeah, the main reason is simpler. Then we can there's a lot of experiments you can do, a lot of everyday, we can compare to our everyday observation more easily using transverse wave, because water wave, guitar string, right, everyone knows, me can talk about violins and pianos and all that. So so that is the case that we will study more frequently. Okay, and then so a lot of the physics about waves is actually, the terminology appears in music as well. So if you talk about harmonics, your tuning frequency has the frequency things, and then overtones, and then yeah, harmonics. What else? There's a lot lah. There's a lot. So definitely I'm live demonstration of propagation in air medium. Yes, as long, yeah, because I'm talking, right? So okay, yeah, so that's all for today. I will continue the rest on the Monday class, right? So we haven't actually derived the wave equation yet, so we will do that on Monday. And what do you mean? This sounds like song lyrics. So yeah, so we're gonna do that on Monday. So I think that's all for today lah. And so right now there's a quiz ongoing. Yeah, don't forget. So remember to do it. and and so yeah, so I'll see you on Monday. So that's all for the class. If there's any question, you can ask me here. I will stick around for a bit more. Otherwise, I shall stop the recording.